Cognitive Psychology by Gilhooly et al. Partial reading of Chapter 1, starting on page 18, Cognitive Neuroscience. The notion that the brain is the source of mental activities and experience is a very ancient one. Around 2,500 years ago, the Greek thinker and pioneer medical doctor Hippocrates gave the idea a very clear statement. Men ought to know that from the brain, and from the brain alone, arises our pleasures, joys, laughter, and jests, as well as our sorrows, pains, griefs, and tears. Through it, in particular, we think, see, hear, and distinguish the ugly from the beautiful, the bad from the good, the pleasant from the unpleasant. Although some ancient authorities, such as Aristotle, proposed that the brain's main function was to cool the blood and argued against the brain as the seat of the mind in favor of the heart, the basic notion that the brain is necessary for mental life has long been widely accepted. As Francis Crick in his book in 1994 put it in terms reminiscent of Hippocrates, your joys and sorrows, your memories and your ambitions, your sense of personal identity and free will are in fact no more than the behavior of a vast assembly of nerve cells and their associated molecules. We will now try to give a broad picture of the brain before discussing particular approaches and methods in the next section. Brain basics. The brain is the central part of the body nervous system. The peripheral parts of the nervous system feed sensory information from external and internal sources into the brain, which in turn sends motor signals to the muscles in order to cause actions, from walking to talking. The inside front and back covers of this book show schematic views of the brain that you may find it useful to consult, as brain areas are referred to in most chapters. If the brain is removed from the skull, it does look rather porridge-like, as has often been remarked. However, unlike a bowl of porridge, it is actually highly structured into distinct parts and subparts. At a very broad level, it is clearly divided into left and right hemispheres, connected by the corpus callosum. As you can see in figure 1.7, four main sections or lobes are apparent in the outer layer, the cerebral cortex, in both hemispheres. The frontal lobes, the parietal lobes, the occipital lobes, and the temporal lobes. Deeper inside the brain are distinct structures such as the thalamus, from Greek inner room, hippocampus, from Greek seahorse, and amygdala, from Latin and Greek almond. At the base of the brain is the cerebellum, from Latin little brain, which is important in movement control. The names reflect the shapes of the structures. Finally, the following terms are often used to indicate locations in the brain: dorsal, meaning towards the top, Latin as in back, ventral, meaning towards the bottom, Latin belly, anterior, meaning towards the front, in Latin before, posterior, meaning towards the back, Latin coming after, lateral, meaning at the side, Latin a side, and medial, meaning in the middle. All these structures in the brain are composed of the same building blocks, that is, the neurons. These are specialized cells that exchange information by transmitting electrical impulses. Neurons are somewhat varied, but typically have a soma, or a cell body, dendrites, which receives signals, and an axon, which transmits signals to other neurons by chemical transmission across synaptic gaps. In addition to the neurons, there are also a large number of support cells, called glia, involved in tissue repair and the formation of myelin. The average human brain has a volume of about 1,400 cubic centimeters and weighs around 1,500 grams. But how many neurons are in the human brain? It is not easy to determine the number of neurons by traditional slicing methods, and von Bartheld et al. Reported that a wide range of estimates had been reported over the years, from 3 billion, made by Donaldson in 1895, to 1 trillion, by Kandel and Schwartz in 1985. Susanna Herculano-Hausel in 2009 pioneered a brain soup method in which brains are homogenized and dissolved in a special solvent so that the nuclei are preserved in resulting soup, which looks like unfiltered apple juice pretty much. Samples are then taken from the soup. The nuclei in the samples are counted and the resulting sample numbers can be scaled up, leading to a best estimate of around 86 billion neurons in the average human brain. The number of glial cells is also estimated at around 86 billion by the brain soup method, although previous methods had led to estimates 10 times larger. Please consult Herculano-Hausel 2016 for more on the brain soup method, officially known as the isotropic fractionator method. Thus, the human brain is a fantastically complex structure composed of approximately 86 billion neurons, each of which may connect with up to 10,000 other neurons. Therefore, the theoretical number of possible patterns of connections is of the order of 100 trillion different patterns. This huge number of possible patterns of connections underlines the brain's ability to encode an essentially indefinite range of knowledge. The question then arises, how can we possibly understand such a complex system as our own brains? We will now look at two main approaches to gain some understanding of how the ultra-complex brain system generates cognitive activity. Cognitive neuropsychology. Cognitive neuropsychology examines the effects of brain damage on behavior with a view to identifying how psychological functions are organized. There are many naturally occurring causes of sources of brain damage, some of which are quite focused and some more diffuse. See Table 1.1 below for major sources of brain damage. Brain damage confined to small regions can produce informative breakdowns in performance. For example, damage to the fusiform gyrus can lead to a loss of ability to recognize familiar faces, but leave a normal ability to recognize familiar objects, suggesting that face recognition is a spatial function distinct from general object recognition. The field of cognitive neuropsychology can be traced back to the work of Paul Broca, who in 1861 published an account of a 51-year-old patient called Le Bon, who had lost his normal speech ability after a stroke many years before, and was left able to say just one word, which was tan. Only the patient's speech was affected, and all other cognitive functions, including understanding spoken language, were unaffected. At a post-mortem examination of the preserved brain, 30 years after the stroke, Broca found that there was a small area of damage or lesion in the inferior part of the left frontal gyrus. This region, now named Broca's area, is vital for speech production. Since Broca's finding, it has become well established that in more than 90% of right-handed people and 70% of left-handed people, language functions are strongly localized in the left hemisphere. Broca's study exemplifies the basic ideas of neuropsychology, which are that most, if not all, functions are linked closely to the healthy working of specific brain areas, and that impairments following localized damage can indicate which areas are important for which functions, and can be informative about how broad functions are organized into narrower functions. Thus, Broca's patient showed that the broad language function could be split into spoken language production and language perception as separate abilities, because the patient could understand speech but could not himself speak. The notion of localization had been developed earlier by Franz Joseph Gall and the phrenological school, which had tried to tie a host of very complex functions and personality characteristics such as prudence, acquisitiveness, destructiveness, sense of justice, and so on to particular underlying brain areas. Phrenologists such as Gall sought to infer from bumps in the skull how well developed the underlying brain areas had become, and suggested, for example, that a large bump just above the left ear indicated destructive tendencies. Recently, it has become possible to examine phrenological claims with data from 5,724 brain scans that included detailed skull measurements and a range of lifestyle measures. This study found absolutely no connection between skull bump measures and any lifestyle scores. For example, there was no connection between the supposed amativeness bump and reported lifetime sexual partners, or between the educability bump and years of full-time education. Although the detailed project of phrenology failed in that skull bumps were not in fact linked to the complex functions as hypothesized, the notion of localization of function has persisted strongly. Since the time of the phrenologist, the idea of localization has become labeled as modularity. The modularity view proposes that cognition involves a large number of independent processing units that work separately from each other and apply to fairly narrow domains, for example, face processing, shape perception, perceiving word meanings, speech generation, and so on. The opposite perspective to modularity is that mental functions, especially complex functions, are not localized but are distributed through the brain. On this view, impairments of mental functions due to brain damage depend on the quantity of tissue destroyed, as a law of mass action stated by Lashley in 1929, and not on the specific site of the damage. Experimental studies on the effects of the amount of brain tissue removed on animal learning lend support to the distributed or mass action hypothesis. Interestingly, the famous case of Phineas Gage, who suffered a passage through his left frontal lobe of a meter-long, 3.5-pound weighted iron bar in an explosive industrial accident, was initially taken to support mass action as he showed no intellectual impairment. However, the personality changes in Gage that became evident soon after the accident, from a conscientious, careful railroad worker to an impulsive individual who lacked perseverance, were later interpreted as indicating localization of executive controlling functions in the frontal lobes. After a further period of time, there seems to have been some recovery of executive controlling functions, indicating a degree of brain plasticity. Overall, human cognitive neuropsychology has found the localization assumption useful in interpreting effects of brain damage, and the general notion of localization underlies much neuropsychological research. Double dissociation. Of particular interest for neuropsychology are cases of double dissociation, in which patients can be found with opposite patterns of impairment in two functions. For example, one case may have impaired short-term memory but normal long-term memory, while other may have the opposite pattern. This would suggest that long-term and short-term memory are indeed separate functions, and not just aspects of a unitary single memory system. Simple dissociations, where patients show an impairment in one function but not in other functions, can also be informative, particularly regarding localization. This was the position with Broca's famous case, discussed above. Brain stimulation methods. Information about brain functioning can also be derived from looking at the effects on behavior of electrical or magnetic stimulation of the brain. The principal methods of brain stimulation are point electrical stimulation of exposed brains during surgery, transcranial magnetic stimulation, or TMS, transcranial direct current stimulation, TDCS. Point electrical stimulation. From 1928 to 1947, American-Canadian neurosurgeon Wilder Penfield applied point electrical stimulation directly to the exposed brains of more than 400 conscious patients during surgery for epilepsy under a local anesthetic to allow the skull to be opened painlessly. During these operations, he obtained hundreds of self-reports of what the patients experienced when stimulated, and also records of motor responses when these occurred. Stimulation was applied by means of a thin wire electrode, and current was initially set low at 0.5 volts. The current would be increased in small steps if no reports of experiences or signs of bodily movements were detected, until a limit was reached or effects were obtained. The reports depended on the exact area stimulated. For example, a patient stimulated on the occipital lobe reported, "A star came down towards my nose," while a patient stimulated on the temporal lobe reported, "I heard music, like the radio." Penfield and Baldry in 1937 plotted the points on the cortex that led to head, shoulder or arm movements when stimulated. These points are shown in figure 111. A similar plotting of sensory reports revealed that the extent of neural representation of sensory information was very large for the tongue, mouth and hands, but quite restricted for large areas such as the skin over the back. These data can also be memorably represented by a neurological homunculus, where body parts are scaled to reflect their representations in the cortex, so that the hands, tongue and face are huge, and the trunk and legs are small. For more on Penfield, see Catani in 2017 and his YouTube video. Transcranial magnetic stimulation, TMS. TMS is a non-invasive magnetic stimulation of the brain caused by rapidly changing electrical current in a coil held over the scalp. This procedure typically produces a virtual lesion by which small cortical areas are temporarily disabled. Transcranial direct current stimulation, TDCS. Transcranial direct current stimulation involves sending a low direct current around 1 to 2 milliampere through the brain by connecting electrodes to the sides of the head. The procedure is completely painless, and the current flow leads to alterations in brain function. Current flow can be anodal, from anode to cathode, or cathodal, from cathode to anode. Anodal flow generally boosts performance, while cathodal flow tends to disrupt performance in a way similar to a virtual lesion in TMS. As an example study, we note that anodal TDCS through the parietal lobe appears to affect performance on mathematics tasks. Recently, neuropsychology has benefited from the development of imaging or scanning techniques that enable researchers to see and accurately measure the location and extent of damage in living patients, rather than having to rely on information gleaned at autopsy. We will now outline some of the main imaging methods. Brain imaging. Broadly, there are two main categories of brain scanning or imaging. These are 1. Structural imaging, which shows the static anatomy of the brain, and 2. Functional imaging, which represents brain activity over time. Over recent years, a number of structural imaging methods have been developed, such as X-ray computed tomography and computerized axial tomography (CAT) scans, which require highly focused X-ray beams to be passed through the body. Magnetic resonance imaging (MRI) is the dominant method currently and provides high-resolution anatomical images. This technique does not involve possibly damaging radiation, but uses radio waves and a strong magnetic field that surrounds the person being scanned as he or she lies in a narrow tunnel-like apparatus. Turning to functional methods, electroencephalography (EEG) and event-related potentials (ERP) give a record of function as a summary of electrical activity over a wide area of cortex measured through sensors on the scalp. The resulting waveforms following particular stimuli are different, depending on factors such as how expected the stimulus was, and so the method is useful in assessing expectancy and other effects. For example, ambiguous words, such as bank, are presented and are then disambiguated as, for example, place money is kept, or side of a river. If the disambiguation is expected from the context, then the waveform will differ from when it is unexpected. The great advantage of EEG and ERP is that they are able to measure the electrical activity of the brain with a precision of milliseconds. However, sophisticated techniques are needed to be able to localize the part of the brain that is the source of the electrical activity, and even when the precision is in the order of centimeters due to the fact that the skull and scalp effectively smear the original signal. An early functional method that gives a more localized picture than does ERP or EEG is positron emission tomography, PET. This requires injection of a radioactive compound into the bloodstream. The scans then measure the blood flow to different regions of the brain. Interpretation is based on the finding that when a brain area is active, more blood flows into it, and thus there is increased chemical activity involving the radioactive compound. Interestingly, a 19th century Italian physiologist, Angelo Mosso, first reported this fact long ago in the 1870s from studies of patients whose skulls had been opened up by accidents so that the cerebral arteries had been exposed to view, and the increased blood flow could be seen. As it happened, although useful, PET scans only show activity averaged over about 90 seconds or longer, thus giving a very crude picture of the sequence of activity. This, along with the need for an invasive injection of a radioactive material, has discouraged the widespread use of PET for general experimental purposes. The currently favored technique for functional imaging is functional magnetic resonance imaging, fMRI. This method does not require injection of radioactive substances and measures the degree to which oxygen in the blood flow is depleted in many areas simultaneously. The more the activity, the more oxygen is taken from the blood by neurons. What is measured in fMRI is known as the BOLD, or blood oxygen level dependent contrast signal. It can show effects over quite a short time scale, such as 1 to 3 seconds, relative to what is possible with PET, and in small areas, approximately 3 cubic millimeters, known as voxels. However, it should be noted that many cognitive processes, as measured by reaction times, seem to take 300 to 400 milliseconds, and so are much faster than the 1 to 3 seconds required for bold signal changes. And a single voxel contains hundreds of thousands of neurons, so the temporal and spatial resolution of fMRI is not yet as high as would be wished. In recent years, results from fMRI brain scans have frequently been reported, or some would say misreported, in the media. In such reports, typically a brain outline is shown on which red blobs are superimposed, reflecting areas of high activation, and sometimes blue blobs to indicate deactivation. In newspapers, magazines, and websites, we are told that such blobs show centers for altruism, criminal tendencies, love, wisdom, and religion, among many other complex functions, including, according to one claim, actual true romantic love for iPhones, as observed by Lindstrom in 2011. An internet search with a key phrase such as brains scans show ... will yield many more examples for the curious reader. However, to really understand fMRI results, it is important to be aware of how these images arise. They are not simple snapshots of brain activity, but rather are highly computed images based on many assumptions. The images are frequently arrived at by a task subtraction method in which the brain activity of all the voxels in the control condition, measured by bold signal, are statistically compared to the brain activity in the corresponding voxels in the experimental condition. If the activity is greater in the experimental condition than the control condition, then it is common to call this an activation. Some of the complexity of dealing with fMRI data is shown in figure 1.16, which shows the probability that a given brain voxel will be more active when a participant listens to a human voice than when they listen to other sounds. While there is a relatively small region where the majority of listeners will show a difference in activation, this region is surrounded by an extensive area where some listeners will show a difference. Why there is this large region where some participants will show an activation remains an open challenge for fMRI. It has been suggested that the reliability of repeated scans is not high. There has also been debate over some commonly used statistical procedures, which have been criticized as overstating the significance of obtained differences by Vull et al., who pointed to the risk of capitalizing on chance. A typical brain volume obtained with fMRI involves tens of thousands of voxels, and when activity in these voxels is compared between experimental and contrast conditions, many differences will prove significant by chance alone. Even when conventional methods of dealing with multiple comparisons are applied, a tendency to report the mean effect sizes for the voxels above threshold significance will lead to spuriously high effects being reported. Some further difficulties with generalizing fMRI results arise from the fact that the environment in which the measurements are carried out is very specific and highly unusual. Lying flat on one's back while keeping perfectly still in the claustrophobic noisy tunnel typical of fMRI machines may well affect how tasks are tackled as compared to typical laboratory or real-life situations. There is evidence that posture affects problem solving. For instance, Lipnicki and Byrne in 2005 found that being supine, that is, lying on one's back, facilitated anagram solving but hindered mental arithmetic compared to upright postures. So results from supine participants, as in fMRI studies, could well be specific to that posture. What might imaging studies tell us about cognitive processes? Despite all the difficulties just outlined, fMRI is now a much-used method, and it is hoped that consistent results will emerge over laboratories as studies accumulate and the implications become clearer. Suppose I had devised a new spatial reasoning task and wondered if people might use verbal reasoning to solve it. I might make an argument from scans to processes along the following lines. 1. Broca's area is known to be activated in tasks independently classed as involving implicit speech. 2. Broca's area is activated in my new spatial reasoning task. 3. Therefore, my new spatial task involves implicit speech. Here is a real example which takes things a few steps further by Ferris et al. 2005. 1. The stratium is activated when animals receive pleasure through rewards. 2. The stratium is activated when rats suckle their young. 3. Therefore, suckling is pleasurable to rats. 4. The stratium is activated less by cocaine injection than by suckling in rats. 5. Therefore, suckling is more pleasure-inducing in rats than is cocaine. In these arguments, we have examples of reverse inference by Poldrack in 2006. That is, going from if a task involves cognitive function 1, then brain area Y is active, and in task B, brain area Y is active, to in task B, function 1 is involved. In strict deductive logic, this is not a valid argument. It is the equivalent of saying, if it's Friday, then Smith eats fish at noon. And Smith is eating fish at noon today. Therefore, today is Friday. But perhaps Smith eats fish at noon on Tuesdays and Wednesdays as well as on Fridays. The conclusion that today is Friday is not necessarily true. Similarly, brain area Y may be active when many different cognitive functions are involved. The reverse inference only works when the if means if and only if. This inference pattern is known in logic as affirming the consequent, and is an invalid argument or fallacy, which we will discuss more fully in chapter 14. However, all the reverse inference arguments are not conclusive or necessarily correct. They can be seen as generating plausible hypotheses for later testing. and this is a useful role that imaging results can play. In our mini example, if brain area Y is active, then function F1 cannot be ruled out, but further independent evidence would be needed to conclude that function F1 is indeed involved in task B. The negative case in which brain area Y is not active would support the valid inference that function F1 is not involved in task B. Overall, then, imaging results often suggest hypotheses for further research rather than being decisive in particular cases. However, for cases when there is controversy over which cognitive model might more accurately reflect human capabilities, it is sometimes possible to design an fMRI experiment to critically evaluate these theories. Furthermore, for specific cases, such as retinotopy, fMRI data has been fairly decisive in mapping out the visual fields in the visual cortex. Imaging methods can also make practical contribution, as is indicated in box 1.5 on the use of imaging in identifying patients in persistent vegetative states who may well be conscious although unable to respond overtly to stimuli. Box 1.5. When things go wrong. Using neuroscientific methods to detect awareness in vegetative states. Following severe brain injuries, some patients emerge from a coma and appear to be awake, but show no signs of awareness and no signs of purposeful behavior in response to external stimulation. In circumstances such as this, there is no guarantee that the patient is not actually aware and just unable to respond normally. Given the application of imaging methods to see specific responses in the brain, these techniques are being investigated as a way of communicating with patients unable to respond in any other way. For example, Owen and colleagues in 2006 used fMRI methods with a female patient who met all the criteria for the diagnosis of being in a vegetative state. While being scanned, the patient and normal control participants were asked to imagine A. playing tennis, and B. visiting all the rooms in their houses starting from their front door. The results were striking, as shown in figure 117. The patient and normal controls showed essentially identical patterns of activation, compared to resting periods, to the two instructions. Imagining playing tennis activated the supplementary motor area, and imagining visiting all rooms at home activated parahippocampal gyrus, posterior parietal lobe, and lateral premotor cortex to similar events in both the patients and the controls. Owen and colleagues concluded that the patient did have awareness of instructions and could demonstrate this by her neural response. The study attracted some criticism in that the patient's response could have been automatically cued by the words tennis and house. However, Owen et al. Were able to show that simply presenting the words without the instruction to imagine the activities did not produce any significant response. The results were confirmed in a larger follow-up with 54 patients and 16 healthy controls. This follow-up study found that 17% of patients who appeared behaviorally to be vegetative were conscious and could reliably produce meaningful responses via an fMRI scanner. One patient who had been diagnosed as vegetative for 5 years was able to answer correctly biographical questions such as whether he had siblings and the last place he had visited before his traumatic accident, by imagining playing tennis for yes and walking around his house for no. The basic finding of covert awareness in around 20% of patients who appear to be completely vegetative has been confirmed in a review of 37 published studies involving 1,041 patients. Owen and colleagues have found similar evidence for awareness in some patients in a vegetative state using the more portable and more affordable EEG methods. This work would lead to ways of communicating with patients who can respond to instructions. Patients could be asked to imagine wiggling their right thumb to signal yes and their right big toe to signal no, and then answer yes/no questions. This method generates distinctive EEG traces in both patients and healthy controls. Thus, a questionnaire could read after yes/no answers from the EEG trace. Another application might be to control machines modified to accept such binary thought signals. As Owen in 2019 has pointed out in a review of this field, sole use of behavioral indicators without brain activation indicators can be seriously misleading regarding awareness in apparently vegetative patients. In light of the findings reviewed here, the diagnostic criteria are being re-examined by the relevant professional bodies such as the Royal College of Physicians in the UK and the American Academy of Neurology in the USA to include brain activation indicators of responsiveness. A major application of this work would be to involve apparently vegetative patients in giving their consent or not to proposed care and management options. Networks and functional integration. Paying more heed to networked as against highly localized activity may yield useful results, and is sometimes referred to as the study of functional integration, as against the earlier study of functional localization. For example, it has become apparent from imaging studies that in resting state many brain areas are active in a correlated way. Furthermore, the use of resting states as control or contrast conditions yielded the unexpected finding of deactivation across a range of brain areas when active tasks were worked on. Subtracting the resting activation levels from the task activation levels often produced negative patterns. That is, large areas of the brain were more active during rest than when a focused task were undertaken. From these results, it was inferred that there is a default mode network, DMN, reflecting internal tasks such as daydreaming, envisioning the future, and retrieving memories. Activity in the DMN is negatively correlated with activity in the other brain systems when people focus on external visual signals. In the infant brain, there is limited evidence of the default network, but default network activity is more consistently found in children aged 9 to 12 years, suggesting that the default network undergoes developmental change. Other networks have been identified by assessing correlations of activity in brain areas. Areas of correlated activity can be regarded as forming networks. Principles among the identified networks are a central executive network linking the dorsolateral prefrontal cortex and posterior parietal cortex involved in higher order and attentional control, and a salience network linking the anterior insula and anterior cingulate cortex involved in monitoring the salience or goal relevance of external inputs and internal brain events. Summary. In this chapter, we have indicated the main areas that cognitive psychology deals with: perception, motor action, attention, learning, memory and forgetting, language, decision-making, reasoning, problem-solving, and emotional aspects of cognition. These topics all involve the processing of information, and cognitive psychology can be seen as the study of how we and other animals acquire, store, retrieve, and use information. These functions are carried out ultimately by brain processes, and so neuroscience studies of the brain, involving functional and structural imaging and case studies of brain damage, are relevant to cognitive psychology. A number of approaches to understanding cognition have been explored over the centuries, including associationism, introspectionism, and behaviorism. The associationists were philosophers who observed their own experiences and set out to specify laws by which ideas became associated with each other. One such law is the law of similarity, by which similar ideas evoke each other. For example, cup and mug. Other laws involve closeness in space or time, so that ideas are often evoked close together in space. Cup and saucer, or time, for example, clouds and rain, became associated. The introspectionists were early empirical psychologists who sought to analyze complex experiences into component sensations using very artificial reports by trained participants. The introspectionist method would not be used with children, animals, people with psychiatric conditions, or anyone not extensively trained in the method, and so was of limited use. Moreover, disagreements about the reports of thought without imagery could not be readily resolved. The focus on analyzing experience continues to the present day using experience sampling methods and ratings of experiences on dimensions such as goal-relatedness, realistic versus bizarre, or degree of visual imagery, and so on. The behaviorist school aimed to overcome problems with introspectionism by focusing on objectively observable behavior and especially on learning in animals. The dominant approach today is the information processing approach, which derives from analogies with computers and computer programs, particularly with artificial intelligence programs. In this analogy, the brain is the hardware on which the cognitive software runs. The emphasis on this approach was typically on thinking and problem solving in the earlier period, but more recently a considerable body of work has developed on learning using connectionist models. A direct focus on the brain and neural processes has grown in the form of cognitive neuropsychology, which focuses on effects of brain damage, and cognitive neuroscience, which focuses on scanning of intact brains performing live in laboratory tasks and on temporary interventions that can affect short-term functioning. A wide range of methods for scanning, as in EEGs and fMRI, are available. Intervention methods that temporarily boost or depress functions such as direct current stimulation and transmagnetic stimulation are discussed. Finally, we note a very useful application in which fMRI traces can be used to tell whether apparently vegetative patients are aware and can be used by patients to communicate their preferences, even although they cannot control any muscles in their bodies, and so cannot communicate by speech or by gestures of any kind.